This video considers the maximum power transfer theorem as regards to AC circuits looking at the reactance. So I've already done a video where I did the maximum power transfer theorem, and that worked for both AC and DC circuits because the only impedance within the circuit I considered was the reactance, or was the resistance. But now we're going to look at both resistance and reactance. So remember, power, when we talk about power, we're talking about real power used. And inductors and capacitors do not use power, they store power. So they store energy. Capacitors store energy within the electric field between the plates, and inductors store energy within the magnetic field generated within the core of the inductor by the current. And so what we want to consider here is if I have a Thevenin equivalent circuit, so this would be like E Thevenin, and I have a Thevenin impedance which includes some resistance, okay, so this is going to be Z Thevenin, and in series with a load. Now the load is going to have some resistance and some reactance. Now that reactance could be capacitive reactance or inductive reactance, or maybe there's no reactance at all and just resistance. And so, like the previous video, we're going to look at various values of this. And maximum power theorem says that maximum power will be transferred to the load. So remember, like if we're trying to transmit our voice or something through the radio, we're going to have an antenna. So what we want to do is get maximum power to the antenna or to the load. So in this case, the antenna represents the load. And so the question is, how do I get maximum power to the load? And that's what the maximum power transfer theorem tells us. But now we've got to deal with reactances. So what I'm going to assume here is that I've got a Thevenin resistance, R Thevenin, and then I'm going to have a capacitor. So I'm going to have a minus J X of C reactance in my Thevenin impedance. And maximum power transfer tells us that Z load should equal to Z Thevenin conjugate. Okay, what that conjugate means is that if we have a capacitor, right, it's a minus J, then we need a plus J of the same value, which basically is telling us if I have a capacitor in my Thevenin impedance, I'm going to need an inductor in my load. And basically the goal then is that the inductive reactance within the load is going to exactly match the capacitive reactance within the Thevenin. And so those will cancel out and I'll be left with just resistances. And then we're back to the example I did during the first video where we only had resistance. All right, so here we're going to have, of course, it's an AC voltage source, so it's going to be 20 volts. There should be a voltage unit here somewhere. It's going to be 20 volts with an angle of 0 degrees. And then, of course, R Thevenin, actually this was R Thevenin, these should be Z's now. So these are impedances, so they're Z's. So they have both resistance and some reactance. Okay, so R Thevenin is going to be given, or excuse me, Z Thevenin is going to be given as a 10 ohm resistor with a 10 ohm reactance, and it's negative, so it's a capacitive reactance. Okay, so that is the Z Thevenin. And again, that Z Thevenin is, by simplifying this complex circuitry inside of some complex device, okay, and down to just a simple impedance with some resistance and some reactance. So of course there's probably some inductance inside of this, and there's lots of resistors in here and lots of capacitors in here. And what we're doing with Thevenin is we are trying to simplify this very complex system down to just a Thevenin voltage supply with a Thevenin impedance, okay? And so in this example, I just picked some easy numbers. So I am saying that I've got a Thevenin impedance of 10 ohms resistance minus J 10 ohms capacitive reactance. And then what I want to do is I'm going to calculate the Thevenin, I'm going to calculate the currents basically based on this circuit for 5 different loads. So I have 5 loads here. One of them is going to have a capacitive reactance that is actually larger than the Thevenin reactance. And so I'm going to use 50 ohms of reactance. And then I'm going to use the exact, so these two impedances are equal. So R Thevenin exactly equals the load, or yeah, Z Thevenin. Okay, let me make this bigger and bolder. This is a Z Thevenin here. Okay, so Z Thevenin exactly matches, right here, Z Thevenin exactly matches Z load. Okay, so and in this second case. In the third case, I'm going to have that the load has no reactance at all. So it's only resistive. Okay, so it's only resistive in the load, but Thevenin, the Thevenin does have that minus J10 capacitive reactance in it. Okay, and then I'm going to do the case where this is the complex conjugate piece here. Okay, so this is the case where, not that one, this one here is the case where it's the conjugate, right? So we have that this is a plus J10 and this is a minus J10, and according to the maximum power transfer theorem, right, we're going to get maximum power to the load So we're going to get maximum power to the load here when these two are the same magnitude, right? So when R Thevenin and R load are equal, and when the X reactance Thevenin is the opposite of the load reactance. Okay, and that's the conjugate. So the conjugate says if you got a minus J in your Thevenin, you need to have a plus J in there. So this is what they're telling us the maximum is going to be right here. Okay, so when you look at that, then when you look at the total impedance, okay, so if we look at the total impedance, where these two are the exact opposite, the reactance goes away. So here the reactance goes to 0. In this case, where we had the minus J10 and the plus J10, then our reactance term disappears. And that's what they're telling us is going to be the maximum power. All right. So in this column here, as you can see, I have the total impedances. Okay, so this is the total impedance, Z total, which are just two series impedances, so they just simply add up. And so we're going to calculate the current, all right? And so if we calculate the current, right, that's just Ohm's law. So we're going to take the voltage E Thevenin, okay, which again does have an angle to it. It's a phasor, it has an angle, right? But I'm using it as my reference, so I'm using an angle of 0. And we're going to calculate our current then. So it's E Thevenin divided by Z total. Okay, that's going to be my impedance. So in the first case, we had 10 minus J10 for Z Thevenin, which doesn't change through this. I keep that the same. But then I had a 10 minus J50. So my total impedance is 20 minus J60. And so if we calculate that, that's going to give me a current of 0.316 amperes with an angle of plus, okay, so remember this is a minus J here, or a negative 90 degree piece, and we're dividing by that, so that's going to give me a positive angle of 71.5 degrees. In the next case, I've got 20 minus J20, right? And we can just guess that's going to be 45 degrees. So that's going to give me a current of 0.707, a current of 707 with a positive 45 degrees. Okay. In the next case, this was the case where the load had no reactance at all. So my total impedance is 20 minus J10, and that's going to give me 0.894 amperes with an angle of positive 26 degrees. Right? And now we're on the fourth case. The fourth case is the one where they're telling us that's actually going to be our maximum. And so when we do that, right, the reactances disappear. So we get 20 volts divided by 20 ohms, which gives us 1 ampere. Okay, 1 ampere with exactly 0 degrees phase shift in there. All right. And then in our final example, we had 20, the impedance was 20, and then the reactances minus J10 plus J50 with a plus J40, so 20 plus J40 for our total impedance. And so our current now becomes 0.447 amperes at an angle of minus, now this is a plus, so it's at an angle of minus 63.4 degrees. Okay, so you can see that we have maximum current now. We're getting maximum current when the inductive reactance and the capacitive reactances are canceling out. We're getting maximum current. Okay, this is also known as resonance here. When the capacitive reactance cancels out the inductive reactance, that's what they refer to as resonance. All right, so total power then, remember that total power, and this is actual power being used. We're not worried right now about the power being stored within the capacitor or power being stored within the inductor. We're just worried about total power being used, okay, which is in watts, and that total power is equal to I squared R. So total power is equal to I squared R. So total power is I squared R. Okay. And so we have now, since voltage and current are in phase in the resistor, okay, so when we're talking about the total power, we're talking about I squared times R, because we're talking about the power being used. So we're not worried about the voltage drop across the inductor, all right? And that's where this equation comes in very nice. I squared R gives us true power being used. And so its total power includes the power here in this Thevenin resistance and in the load resistance, okay? But it doesn't include power being stored within those inductors and that sort of thing. All right, so if we look at the total power, it's I squared times R total. Okay, so R total is given here, and in this example I'm not changing R total. I changed that in the previous video after we got the reactance to 0, or we started out with no reactances actually in that video. So if we look here now, looking at total power, I'm going to be using a total of 6.32 watts. Okay. Remember, it's I squared, so 0.316 squared times 20. Okay, that's going to be my total power. So for the first case, 6.32 watts. For the next case, it's going to be 14.1 watts. Okay, so power is going up. For the next case, it's going to be 17.8 watts. And for the case of maximum power, right, I'm using my supply. This is my supply, right? This is total power that this guy's got to supply. And that guy's going to be supplying exactly 20 watts. All right, and then if we look then at the final case, we're back down to 8.94 watts, okay, for total power. All right, so this is the total power being used, or being supplied, excuse me. This is, yeah, it's the total power being supplied, which means some of it's being used in this Thevenin resistance, and some of it's being used in the load resistance. Okay, it's total power being used within the entire system. All right, so now let's look at the power that's actually being used in the load itself, okay, which would be the actual power of transmission if we think about this radio transmitting a message. So the total power to the load is the load resistance. So we got to come back to the load resistance. Now again, we're not concerned about anything being stored within a reactance, but just that. So that's still, it's I squared times the resistance at the load. And so we're going to have then our total current 0.316 squared times the load, which is just 10. All right, and so that turns out to be about 5.10 watts. And then if we look at the next case, okay, then we're going to find that we're using about 7.07 watts. And if we look at the third case, we're actually going to be about, turns out to be exactly 8 watts. And now if we look at the case where our reactances were canceled, our wattage jumps all the way up now to 14.1 watts. Okay, so 14.1 watts is being used here at the load. And then if we look at the very last case, Okay. All right, so now we're going to look at the total power, right? And total power is I squared times R total. Okay, so that's the total resistance. Okay, the total resistance is the combined resistance through our Thevenin and plus our load, because they're just series resistors up here. So we have I squared R total is going to give us our total power. All right, so our total power is going to be 2 watts for the first case. So we take 0.136 squared times a total of 20. And so if you, if it may be a little bit off here because we rounded off to 3.16, okay, but if you take it out to, at least 5 or 6 decimal places, which I didn't record here, it actually comes up to be 2 watts. Likewise, if you do the next case of 0.707 amperes with a Z total of 20 minus J20, then that's going to give you a total power of 10 watts. And if you do the next case of 0.894, that's going to give you 16 watts. And if you do the case here at max power, this is 1 ampere squared times 20 ohms total. So that's going to, of course, be 20 watts. And if you look at the following case, we're going to be back down to 2 watts. Or excuse me, total is going to be 4 watts. Okay, so the total is going to be 4 watts in this last case. All right, so now let's take a look then at just the load power. Okay, so the load power is your current squared times just the load resistance. And now remember, the load resistance was simply 10 ohms. We didn't change the load resistance. That was 10 ohms the entire time. And so we take this current, square it, times 10 ohms. And so that gives us 1 watt for the first case. For the second case, we're going to have 5 watts. For the second case, we're going to have 8 watts. Right? Now think about this. We've got resistance here, and you got the same amount of resistance here. And so for your current, it's going to be half of that. All right, so that so if we look at the max power case, right, we're going to be getting 10 watts, and we're going to be getting 2 watts on this last condition. But hopefully, right, you can clearly see now that maximum power is occurring. So the maximum power here is occurring at the point where Z Thevenin is the complex conjugate of Z load, so that the capacitive values and the inductive values are equal, but they're opposite signs, and so they cancel out. And that gives us the maximum power to the load.